put down some waveforms and let us find out first of all what kind of harmonic components are present, making use of the various symmetry conditions that we have discussed. Suppose we have this kind of waveform. Using the symmetry conditions, identify the terms present in the Fourier series, or you can say what are the terms that are absent in the Fourier series. So, if this function is there, first of all you can straight away see this is an odd function because f of t equals minus f of minus t, therefore only sign terms are present. And further, whatever waveform you are having here is repeating in the next half cycle with a reverse sign. Therefore, this has the half wave symmetry of the type which we have talked about. So, the result is that this can have only sign terms, but odd harmonics. So, odd ordered sign terms are present. In this waveform, you can't expect cosine terms, you can't expect second harmonic, fourth harmonic and so on, certainly not DC. Suppose I shift this waveform and have something like this triangular wave with symmetrically situated at the origin, then what we have, this is an even function of time, therefore cosine terms are present, but that half wave symmetry we talked about still persists. This whatever occurring in this half cycle will repeat itself, therefore we can say now it will have odd ordered cosine terms only are present. We must carefully distinguish between the oddness and evenness of the function and the oddness and evenness of the order of the harmonic, right. When you are cosine terms you say it is an even function, when sine terms only is an odd function, that relates to the function itself f of t and f of, whether it is f of t equals f of minus t or minus of f of minus t. What we are talking about is the order of the harmonic, the index of the harmonic, second harmonic, fourth harmonic or even ordered harmonics, and fundamental, third harmonic, etc. are called odd ordered harmonics. Suppose I have a function like this, which is the same function shifted upwards by a certain amount. So, in other words, if I draw a line here parallel to the x axis and subtract this value from this f of t, this will be the resultant. So, what do we conclude from this? It will have all the harmonics that we are having here plus a DC term, right. So, you have, because if you subtract this value from this, then the resulting waveform will be exactly this, right. Therefore, we have DC plus odd ordered cosine terms. Only will be present. So, similarly, if this waveform is shifted up, so if this is the line, then you have, if you subtract that amount, this value from the waveform, you have a waveform which is given in A, therefore, you have DC plus odd ordered sine terms. One thing you would notice from this example is that a same function, if we shift the origin, in one case it may be an even function, in other case it may be odd function. Therefore, the placing of the origin plays an important role, but that does not affect the amplitude of the harmonic, as we will see a little later. And once again, it is also possible for us to note that when you remove the DC term from a given signal, sometimes you find out certain characteristics which may not be present in the original signal, as this example shows. Now, let us work out another example. So, a waveform is given only for this interval of time. Now, certain additional conditions are given and we are asked to find out, identify the complete waveform, right. So, let us say the conditions are f of t has only odd ordered sine terms. So, if the waveform for the entire cycle is not given, only partial specifications are given, but this condition is given. So, this is the data that is given to us. So, if f of t has only sine terms, which means the function is odd, therefore, if 0 to t by t naught upon 4 is prescribed to us, we immediately conclude that this must be its image on the negative time axis. So, this portion we can fill up because only sine terms are present, and then we are also given that it has odd ordered harmonics only, which again tells us that whatever sequence of values it takes in one half cycle is getting repeated with a negative sign in the subsequent half cycle. So, starting from this, in this half cycle this is the sequence of values, therefore, the negative of that would be this, and therefore, this also gets filled up. Now, that corresponds to 3 t naught by 4. So, we have completed the waveform for a full cycle, right. So, we can make use of the conditional symmetry and then extend this to satisfy this the given data and the conditions that are given. So, suppose it is said that f of t has odd ordered sine terms, cosine terms, then how does it go? This is the waveform that is given to us, and since it has only cosine terms, it is an even function, therefore, this would be the situation from minus t naught upon 4 to t naught upon 4, and since it has only odd ordered harmonics, this entire waveform gets repeated with the negative sign. So, this is the extension that we are having, and that would be the situation for a case where f of t has only odd ordered cosine terms. Let us have another example. We will take the square wave, which is a very important waveform. of course it repeats itself in the negative time also like this, and we are asked to find out its Fourier series expansion. We can see straight away that the positive half cycle and negative half cycle have equal areas, they cancel each other out. Therefore, the average of this function f of t over a complete period is 0. Therefore, a naught is 0. We also can see without further ado that Bn is 0 because the function is, I am sorry, the function is odd, therefore, An is 0. So, the only coefficients that can be present are the B coefficients. So, Bn would be 2 upon T naught, 0 to T naught upon 2. I will break up this integral into two parts. From 0 to T naught upon 2, the value of the function is a sin n omega naught t dt plus T naught upon 2 to T naught. In this interval of time, the value of the function is minus a sin n omega naught t. You can evaluate this second term to the two integrals separately and then arrive at the result. Alternately, we can also make use of one property which we have discussed already. When we are talking about half wave symmetry conditions, we said it is exactly the situation where whatever is happening in positive half cycle will occur in the negative side in the second half cycle. Therefore, at that time, if you recall, exactly similar situation, we said this integral is equal to this integral for odd n. Therefore, we can as well write this as, for odd n, this will be 4 by T naught times this. Alternately, we can calculate this also independently. So, we can write this for 4 by T naught 0 to T naught upon 2 a sin n omega naught t dt for odd n only. We must be very careful in writing this. You can't have this and then evaluate for even n, it will give a result, but that is wrong. For even n, this term will cancel with this and that becomes 0. So, when you write this expression, you must make sure that you know that it is valid only for odd n only. This is 0 for even n. So, if you work this out, then it will be Bn will be for odd n 4a by T naught 0 to T naught upon 2 sin n omega naught t dt. So, 4a by n omega naught t cos n omega naught t 0 to T naught upon 2, right. Therefore, this will be 4a by omega naught t is 2 pi, T naught omega naught T naught is 2 pi, so 2 pi n, and here you have 1 minus cos n omega naught T naught by 2. Therefore, this is 4a by 2 pi n times cos n omega naught T naught by 2 is cos n pi, and we are talking about odd n. So, cos n pi will be -1 and therefore this will be Fourier by n. So only Bn terms is present. So finally we conclude that the Fourier series expansion for this would be, I'll write here, f of t Fourier by pi sin omega naught t plus Fourier by 3 pi sin 3 omega naught t plus Fourier by 5 pi sin 5 omega naught t, etc., etc. So this is a important result that it would pay us to keep this in mind. For a square wave like this with an amplitude a, the fundamental component has an amplitude 4a by pi. So that means the fundamental will be something like this. The third harmonic will be having 1/3 that amplitude. So it will be fifth harmonic will be 1/5. Actually the figure which we have seen in the earlier lecture corresponds to this. So the amplitudes go down inversely as the order of the harmonic. We will continue this discussion. To sum up, first of all, what we have learned in this lecture is that the symmetry coefficients, symmetry conditions on the given function of time enable us to calculate the Fourier coefficients with less effort than would otherwise be necessary. In particular, we saw if the function is even, then there can be only cosine terms present. If the function is odd, that if f of t is minus of f of minus t, only sine terms can be present. And the third type of symmetry that we talked about is when whatever waveform you have for one half cycle is repeated for the subsequent half cycle with its negative sign, then we call that half wave symmetry. It is quite common in electrical machines, for example, and in that situation we have only the odd ordered harmonics. We have the fundamental, the next harmonic is the third harmonic, fifth harmonic, and so on. There is another kind of symmetry which we mentioned in passing, that is when the function repeats itself identically for every half cycle. In that case only the even ordered harmonics are present, that means the second harmonic, fourth harmonic, and so on. This, as I said, is, we call this function to have a period twice what we normally expect, half of what we twice as we normally expect, because this is usually derived from another signal whose fundamental frequency is already defined. Using these symmetry conditions, we worked out a few examples which show how the Fourier coefficients can be evaluated, making use of the various symmetries that are present. In the next lecture, we will talk about another method of setting up the Fourier series, not in terms of trigonometric functions, but in terms of exponential functions, which will give a more compact notation and certain advantage in the computation. This we will take up in the next lecture.